So we are now going to develop ways to essentially quickly rationalize and develop ways of figuring out what the 3D geometry of each molecule is. And let's start with something simple. We have a central atom with atoms or lone pairs bonded to it. And by molecule, I mean it can be a molecule or a polyatomic ion. And we're looking at it from the perspective of one central atom first. Now, about a particular central atom, there will be electron domains. There will be regions of high electron density. A bond, which can be a single bond or double bond or triple bond or what have you, or you have lone pairs. You can therefore figure out what the geometry is by theorizing that the electrons are going to repel each other. So these electron domains are going to take up shapes such that they are as far away apart as possible. And in this case, we can model them using balloons. So here I have my central atom right where the knots are on these balloons. And each of these balloons represents an electron domain. Remember, I don't care if they are double bonds, single bonds, triple bonds, or lone pairs. Each of those count as one electron domain. So for example, if I have a double bond and two single bonds, that is 3 electron domains about the central atom. So let's look at the shapes. Here I have 2 electron domains, 1, 2, about the central atom here. And in this case, you see that they are pushed apart with a 180-degree angle. They're in line with each other. Therefore, we have a linear geometry with a 180-degree bond angle when you have 2 electron domains. What if we have 3? Here we have 3 electron domains, 3 balloons. You see that they're in a plane with each other. And there's 1, 2, 3, kind of in a triangle, right? It's going to be 120 degrees between each of them, just by symmetry, approximately. So 120 degrees in the ideal case. We call this geometry the trigonal planar geometry. If I have 4 balloons, here you can see that it kind of sits like a pyramid with a triangular base. This is the tetrahedral shape. And the angle going from here to the central atom to another electron domain is 109.5 degrees in the ideal case. What do we have 5? We have 3 and 2. Let's put them together. So now I have 5 balloons. And how it turns out is that we have what's known as the trigonal bipyramidal shape. Because if I look about this triangular, I have a triangular base here and consider this a base. I have one pyramid pointing upwards here, and one pyramid pointing downwards here. So therefore, I have 2 types of positions here. I have the equatorial positions. If I look at this, I have these 3 in darker blue, and they're in a plane with each other, just like the trigonal planar shape, with a 120-degree angle between them. In turn, if I look here, I have 2 axial positions, and they form a 90-degree angle here, with those in the equatorial position. Finally, if I have 6 electron domains, then I have 6 balloons here, and you can see that I have an octahedron, where I essentially have like a Cartesian, like the Cartesian axes, we have balloons, essentially, or electron domains rather, at 90 degrees to each other.